Hello everyone. This is our sixth lecture of complex integration in the course 19 MA 204 complex variables and ordinary differential equations. So in this lecture we are going to discuss about evaluation of real definite integrals by using contour integration. So what do you mean by contour integration? So the complex integration along the curve used in evaluating the definite integral is called contour integration. So that means we are going to convert the definite integral into complex integration form and then evaluating that particular integral, that is called contour integration. So we are having three categories under this contour integration. The first type is integration. The given integration is in the form integral 0 to 2 pi function of cos theta comma sin theta, which means integration limit they must give 0 to 2 pi and function containing cos theta or sin theta, theta form. Function is in terms of theta form, also which containing cos or sin term, means that comes under the type 1 category. And we are going to convert that into complex integration form, that is a closed curve integral over closed curve C form. Type 2 is function integration limit must be minus to plus infinity, otherwise 0 to infinity means we need to multiply 2. So minus to plus infinity function of x by function of x form, that means both numerator and denominator containing x terms, means that comes under the second type category. The third type also function in terms of x alone, but sine or cos terms involving in terms of x, sin x, sin 2x, sin ax, something like that. So function as well as the trigonometric term in terms of x comes, means that comes under the third category. The second and third limits are minus to plus infinity, otherwise in some cases they may give 0 to infinity also. And the first is purely function containing theta form. So all the three types we are going to convert the given definite integral into the complex integration, and then we are going to evaluate by using the Cauchy residue theorem. So look at the first type category. The first type is integration is of the type integral 0 to 2 pi f of cos theta comma sin theta form. So here I am going to use the substitutions for converting this definite integral into complex integration. Put z equal to e power I theta. While I am differentiating this with respect to theta, I will get dz equal to a differentiation of e power I theta, which comes I into e power I theta into d theta. Both taking differentiation on both sides, I will get dz by d theta, here I into e power I theta. So d theta comes into the right hand side, I will get dz equal to I into e power I theta into d theta. As well as d theta, after simplifying this, d theta is equal to dz by I into e power I theta. So therefore we are taking e power I theta as z. So after replacing it, I will get d theta is equal to dz by iz. So next also we need to use the substitution for cos theta and sin theta. Cos theta we know very well. Cos theta formula is e power I theta plus e power minus I theta by 2. We are taken e power I theta is equal to z. While I am replacing it here, I will get e power I theta is equal to z, and e power minus I theta is nothing but 1 by z. I am taking this 1 by 2 out. Likewise sin theta also. Sin theta formula is e power I theta minus e power minus I theta by 2i. So I am taking 1 by 2i out. I will replacing e power I theta into z and e power minus I theta into 1 by z. I will get the replacement for sin theta is equal to 1 by 2i into z minus 1 by z. These two are replacements for sin and cos theta. Next, after replacing it into the given definite integral, I will get the integral 0 to 2 pi, it will be changed into the complex integral over C, f of cos theta values here and sin theta values here and d theta value. D theta is dz by iz. The closed curve C is nothing but unit circle. In this type 1, we are taken the closed curve C is an unit circle, modulus of z equal to 1. Let us move on to the problem under this category. Evaluate integral 0 to 2 pi d theta by 13 plus 5 into sin theta. So this is purely comes under the type 1 category because the limit is 0 to 2 pi and the function in terms of theta also sin theta involving. So therefore this comes under the first type category. We are using the substitutions in this particular type is z equal to e power I theta. So like a way dz equal to I into e power I theta into d theta. So from this I will get d theta is equal to dz by I into e power I theta is z. So therefore d theta is equal to dz by iz. We are going to change it the given integral into complex integration. Complex integration in terms of z only, that's why. Next, sin theta is involving in this particular problem. So we need to find out sin theta value. Sin theta we already know very well. So 1 by 2i into z minus 1 by z. I'm going to use these substitutions into the given problem. So the given problem can be converted into is the form integral over c. This definite integral will be changed into complex integral over c, and d theta value dz by iz 13 plus 5 into sin theta values 1 by 2i into z minus 1 by z. I'm going to simplify the denominator. So while I'm taking LCM z minus 1 by z, I will get z square minus 1 by z. Here I'm getting 5 by 2i. I'm multiplying this 5 inside. Next, I'm taking this 2i into LCM. I will get 26 times of iz. 26, yeah, 2iz LCM edukum. I'm going to take it 2iz LCM. I will get 26zi plus 5z squared minus 5 by z. I'm taking this 2i out. Therefore, this simplification gives z getting cancelled, I getting cancelled. I will get 1 by 2. 1 by 1 by 2 become 2. So that will come here. So dz by, in the denominator I am having 26iz plus 5z square minus 5. So this is in the form of integral over c f of z into dz. In place of f of z I am having 1 by 26iz plus 5z square minus 5. So I am going to solve this integral by using Cauchy's residue theorem. So here f of z is equal to this particular term. This looks like an quadratic equation, quadratic equation in z. This factorization form is z plus 5i into 5z plus I. After multiplying these two, I will get back this previous one. So next, I am going to find out for using the residue theorem. First step, I need to find out the poles. Next, residues for the corresponding poles. So before finding the residue, we need to check each and every pole lies inside the given region or outside. Suppose the particular pole lies outside, means that corresponding residue value is 0. So next, after factorizing, the poles are, so for finding poles, we need to equate each and every factor into 0. What will you get for z after equating the first factor into 0? I will get z equal to minus 5i, no? So minus 5i is one pole. So in the second term, I am equating into 0. I will get z equal to minus I by 5. So that is second pole. Because while I am replacing this z value into this particular term, I will get 1 by 0. That is infinite. So that is called pole. Okay. So z equal to minus 5 is a pole. So given region C is a closed curve, C is nothing but a unit circle in this particular type. So therefore, minus I definitely lies outside the unit circle modulus of z equal to 1, because modulus of z is a unit circle, center 0, 0, all the sides radius is 1. Here z equal to minus 5i. Minus 5i lies definitely outside. Minus 1 by 5, this gives some 0 point value. So this is lies inside the unit circle, modulus of z equal to 1. So therefore, automatically I am going to take z equal to minus I, 5i, residue value is 0. We need to find only for z equal to minus I by 5. Both order is 1. So therefore, the next step to find the residue of f of z at the poles which lies inside alone. So here z equal to minus I by 5 only lies inside. It is an order of 1. Simple order pole. Therefore, the formula is limit z tends to a, z minus a into f of z. A is equal to minus I by 5, minus into minus plus 1 by f of z factorization form is z plus 5I into 5z plus I. While I am taking in the second factor 5 outside, I will get z plus I by 5. So after taking 5 outside, I may cancel out z plus 5I, z plus 5I. I will get the remaining terms or 1 by 5 into z plus 5I. Now I am replacing z value in this particular factor. I will get minus I by 5 plus 5I. So after simplification gives the value 1 by 5 into, I am taking LCM, minus I plus 25I by 5. So the final answer is 1 by 24I. This is the residue value of the corresponding pole z equal to minus I by 5. Next, I am going to use the Cauchy's residue theorem. Integral over C f of z dz equal to 2 pi I into sum of the residues of f of z at its corresponding pole lies inside the given curve C. So therefore, we are getting only one residue value, another one is 0. So therefore, substitute that particular value here. I will get 2 pi I into 1 by 24I. So I getting cancelled. 2 by 24 is 12. So pi by 12 is the answer for integral over C f of z dz. But we need to find out the given integral 0 to 2 pi d theta by 13 plus 5 into d theta. That is nothing but we are converted into 2 times of integral over C f of z. So this particular value, integral over C f of z dz value is pi by 12. I am substituting here. I will get the final answer for the given definite integral is pi by 6. So this is our final answer. So let us move on to the next problem. Evaluate integral 0 to 2 pi cos 2 theta into d theta by 5 minus 4 times of cos theta. In the numerator also containing one more cos theta term. So for transferring this given definite integral into complex integral, we need to use the substitution z equal to e power I theta, because the given we are going to take the complex integration C is the closed curve modulus of z equal to 1. That's why z equal to e power I theta. dz equal to I into e power I theta into d theta. So d theta value is dz by iz. Like a way, I need to find out cos theta value, because cos theta is involving in this particular given problem. So cos theta we know very well, 1 by 2 into z plus iz. So we also need cos 2 theta value. For finding that, I am squaring z square. Z square value is e power 2 I theta. So e power 2 I theta means what? Cos 2 theta plus I sin 2 theta, because e power I theta is cos theta plus I sin theta. E power 2 times of I theta means cos 2 theta plus I sin 2 theta. So this is nothing but, cos 2 theta is nothing but real part of z square, right? So real part of e power 2 I theta, which means real part of z square. This is equivalent to z square. So therefore, in place of cos 2 theta, I need to replace real part of z square. So next step, we are going to converting the given integral into contour integral, which means complex in complex form. So given integral is here. So the limit will be changed into closed curve C. In place of cos 2 theta, we need to replace real part of z squared by 5 minus 4 times of cos theta value is 1 by 2 times of z plus 1 by z. After taking LCM, I will get z square plus 1 by z, and d theta is dz by iz. So next, I am simplifying the denominator. Look at here, z square by z getting cancelled. I will get z. Okay. So after taking LCM in the denominator, I will get 5z minus 2z squared minus 2 whole divided by z. That z getting cancelled. The numerator I will get z square. I am taking this 1 by I outside. So therefore, this looks like integral over C f of z dz form. I'm going to find out this integral value by using the Cauchy residue theorem. And finally, I'm going to substitute that value in this place. So throughout, I'm taking minus outside because z square containing minus. So therefore, after taking minus outside, I'll get real part of minus 1 by I into z square dz by 2z square minus 5z plus 2. So find this integral by using Cauchy residue theorem. Cauchy residue theorem statement is 2 pi I into integral over C f of z dz equal to 2 pi I into sum of the residues. Okay, so find this integral value and finally replace that particular value in this place. So f of z is equal to this particular one, z square by 2z square minus 5z plus 2. So I'm finding for finding the pole, first factorize this denominator. After factorizing, I will get z minus 2 into 2z minus 1. Here the poles are, after equating each factor into 0, I will get z equal to 2 and z equal to 1 by 2. Definitely z equal to 2 lies outside the unit circle mod z equal to 1 and z equal to 1 by 2 is a 0.5. Of course, it lies inside the unit circle modulus of z equal to 1. Now, I'm going to find out the residue for the second case because z equal to 2, residue value is 0, that is lies outside the unit circle. Now, residue of f of z at the point z equal to half is limit z tends to half, z minus half into f of z. In the second factor, I am taking 2 outside. It may get cancelled with z minus 1 by 2. So otherwise, here I am taking LCM, 2z minus 1 by whole divided by 2. Now 2z minus 1, 2z minus 1 getting cancelled. I will get the remaining terms or z square by 2 times of z minus 2. Now I am replacing z equal to half. After simplification gives the value minus 1 by 12. Therefore, the integral over CF of z is equal to 2 pi I into sum of the residues. Residue values minus half. So therefore, this integral value is minus pi I by 6. Substitute this into this particular equation. So we will get minus 1 by I into minus pi I by 6. This is the answer, pi by 6. Here there is no I. This is our final answer. So therefore, the given integral 0 to 2 pi cos 2 theta into d theta by 5 minus 4 into cos theta is equal to pi by 6. Thank you guys.